the formula required to design intermediate stiffener. Okay, now today I will explain the procedure for the design of intermediate stiffener and how we can carry out the design. So whenever I am talking about the design of intermediate stiffener, so it means that we are supposed to select two things. Number one, spacing between the stiffener, spacing of stiffener, and number two, okay, gentlemen, please hold on. What we want to achieve. Actually, in design of intermediate stiffener, the first thing is that we want to decide spacing of stiffener. And the second thing is what would be the cross-section area of intermediate stiffener. So the first thing we need to clear up that why we designed the intermediate stiffener. So we designed the intermediate stiffener to increase the shear capacity of web. Because earlier we have studied that in plate girders, our web is always slender. Slender means that web is very thin and most probably it will always undergo buckling. So that buckling will occur at a stress value much lesser than yield shear stress. So it means that if the cylinder web is not having sufficient shear capacity, or if the shear capacity or the buckling strength of web is less than applied shear, then in that case we need to improve the shear strength or enhance the shear strength by deciding the spacing of intermediate stiffener and by selecting the cross-section area of intermediate stiffener. All and we have discussed. So this was example number 6.1, so where we have proportion the plate girder. So for the same plate girder, and if for the given loading, if we know this shear force diagram, which means that this plate girder is subjected to this applied shear. So for example, the maximum shear force which is acting in the plate girder is 1519. So first of all, we need to evaluate that what is the shear capacity of the web without stiffener. If the capacity of plate girder without stiffener is more than 1519, then we do not require any stiffener. But if the capacity or buckling strength of web is less than applied shear, so in that case, we need to decide the spacing of web panel by providing intermediate stiffener to enhance its shear capacity. So that the shear capacity should be more than applied shear. So today we are going to learn this procedure, how we can decide the spacing of intermediate stiffener first, and then how we can decide the cross-section area for the intermediate stiffener. So first of all, maybe I would like to show you one diagram, then I will be back. So what we do, so last time, yes, this is the final diagram, but I don't want to discuss first. Okay, this one. So actually, we already know the location of bearing stiffener. Bearing stiffener, they are provided above this force reaction and underneath concentrated force because they are provided to avoid the web from crushing or crippling failure against the concentrated force. And then we need to decide the spacing of intermediate stiffener depending upon the applied shear. So what procedure we need to adopt that we are going to discuss. So here you don't need to memorize this design flow because this complete design flow is also given in LRFD design aid from page number 325 to onward. So you need to follow that design flow. So it was given on page number maybe 330. So let me find the design procedure for the page builder. Supposed to be here. Some page are there missing. Yes. From page number 293. Yes, here. From the page number 293 to onward, we are having this complete design procedure. So you can consult this design flow during the examination. You just need to understand that what are the values you need to substitute in this situation. So you need to follow this complete design flow that I am going to explain. So from the page number 293 to onward. So I will explain from here my slides. So first of all, when you want to start the design of intermediate stiffness, so you need to check the height of the web over thickness of the web ratio, which is the lambda W value, B over T ratio of web. If this value is less than 2.46 under root E over Fy, which is 63.54836 T, then it means that in that case, CV value will be equal to 1. It means that web will be quite compact and web will always fail due to shear yielding. For example, you are already familiar with this formula. So shear capacity is the function of shear strength into area of the web multiplied by the shear coefficient, CV value. So this CV value will be equal to 1 when the web is compact. And I believe that you are familiar with this equation because you have been using in the design chapter. So if this condition is satisfied, then CV value will be equal to 1. And then you can determine shear capacity by this formula. So the CV prime is the capacity contributed by tension field action. If we are not providing intermediate stiffness, so CV prime will be equal to 0. So you can determine the capacity by this formula. So the shear strength is taken approximately 60% of normal strength for tensile strength. Phi value will be 0.9 and area of the web is equal to height of the web into thickness of web. And then you can determine the shear capacity. And if this shear capacity is more than VU, then we may not require the intermediate stiffness for plate builder. But if this condition doesn't satisfy, it means that CV value will not be equal to 1. It means that web will not fail due to shear yielding. Rather, the web will fail due to buckling, and that buckling stress will be much less than shear stress. So in that case, we need to see that what is the applied shear. For example, we need to compare this equation. We will compare the applied shear with the shear capacity. And shear capacity, we are going to use this formula. So VU value you will get from shear force diagram. For example, I have already shown you this shear force diagram. Here, for example, what is the maximum shear induced in our plate builder, which is 1519. This means that the shear capacity of web should be more than 1519. So for this, we will see that how much CV value will be required. For this case, we will determine that how much CV value is required. So it means that we are replacing 5V Vn with VU. We know 5 value, we know 0.6 Fy, We know height of the web and thickness of the web, so we will determine how much CV value is required. So from here, by equating, we can determine CV value required. And after determining the CV value, actually what we are going to do? Actually, we are having three formula for CV value that we have already discussed earlier. So this CV value, if we know, so CV value is the function of KV value. Because of this case is not applicable because CV value is not equal to 1. So CV value is the function of KV value, both in equation number 3 and equation number 4. So if we know the CV value, let's suppose I discuss this formula. If I use the equation 4, if I know CV value that I have determined from this equation, then only unknown is the KV. So by solving this equation, because I know CV value, I know 1.51, and I know the E value, height of the web over thickness of the web is also given, Fy is also given. So I can determine KV. And if I know the KV value, so I can use this equation. So if the KV is known, height of the web is known, then I can determine the spacing of stiffness. Because KV value is the function of spacing of stiffness. And if I know the spacing of stiffness, then I can determine KV. If I know the KV value, then I can determine CV value. But I'm proceeding toward the reverse. I'm doing the reverse procedure. But the question arises that if I know CV value, so which formula I should use to determine KV value? The equation number 4 or equation number 3? So actually, equation number 4 is more critical because this equation gives the least KV value or least CV because that is corresponding to elastic buckling. So first, we assume that height of the web over thickness of the web ratio is more than this parameter because KV is unknown. So we will assume this condition and we are going to use this equation to determine the KV value, just like here. So we are assuming that height of the web over thickness of the web ratio is more than 1.37 times under root kV E over Fy. So using equation number 4, we can determine kV value because CV value we have just determined from here. So this equation has, we have got this equation from here by cross multiplication. We have represented this equation in terms of CV because we want to determine the kV value. So if we know the kV value, so first we assume this parameter. Now we can actually compute this expression because we have determined kV here. So substitute the kV value, compute 1.37 and recheck this condition. If this condition is satisfied, means that 1.37 under root kV into E over Fy, this parameter is still less than height of the web over thickness of the web ratio, then KV value that you have computed is the final. But height of the web and thickness of the web comes lesser than this parameter, then you need to revise KV value by using equation number 3 because now this condition will be applicable. So you will revise the KV value by using equation number 3. So you will substitute CV value here and then you will compute KV value from equation 3. But most of the time this condition will satisfy equation number 4. And next, when you have determined the KV value from here, so if this KV value is equal to 5, so KV value is 5, for example here, in which case KV value will be 5? KV value will be 5, then we do not require any stiffener. So if KV value is 5, then we will provide the stiffener at maximum spacing. So maximum spacing is we got from these two expressions. So maximum spacing is lesser A value out of these two equations. So A over H ratio or A should be more than 3H or A should be equal to 260 divided by height of the web over thickness of the web ratio whole square multiplied by h if h go to the other side. If kV value is coming out to be 5, then spacing of stiffener is the lesser value out of these two expressions because we know the height, so you can determine the A value. And also in this equation, you know the height of the web and thickness of the web, so you can determine A value. So if kV requires 5, select maximum spacing or A over H ratio smaller out of 3 for this expression. But if kV value is more than 5, then we are using this equation, substitute the kV value here, and determine the spacing of stiffness from here. So this equation is the simplified form of this equation. So this is the equation of kV in terms of A over H. So this is the same equation we have represented A over H ratio in terms of kV value. So if you are substituting kV value, so you can determine the A value. So this A value, the spacing of stiffener that you have computed, it should be compared against the maximum spacing of stiffener. So this expression is the same that is here. So spacing of stiffener should be less than the A maximum that we have got from this equation. So A value that you have computed, it should be less than this A maximum. And A maximum is 1.5 in AASHTO specification. So maximum A should be lesser out of these two. Actually, for the first intermediate stiffener, first, because we provide many stiffener, intermediate stiffener. So first stiffener is provided at a close spacing to the bearing stiffener. So for the first intermediate stiffener, AASHTO says that spacing of stiffener should not be more than 1.5 H. And AISC says that spacing of stiffener should not be more than this parameter. So this equation is got from this expression. So this is the AISC condition. A over H should be more than 3, but AASHTO says that it should be restricted to 1.5. So if the A value that you have computed from here is lesser out of the least value from these two equations, then A will be fine. So A value that we have computed from here should be less than this value. So let me do this maximum from here because we are just computing the A value from here. So this A value should be lesser than these two A maximum. Otherwise, we will provide the A value equal to A maximum. Okay, after that, we have selected the A value. So for the A value that we have decided, you will recompute the kV value by using this expression. And from this expression, kV value, if you know, you will check the condition whether height of the web over thickness of the web ratio is more than this parameter. So if it is more than this parameter, you will recompute CV value from equation number 4. But if height of the web over thickness of the web ratio is lesser than this parameter, then and more than this, then you will compute CV value from this equation number 3. And then you will verify the shear capacity by using this equation. And if this shear capacity is more than VU value, then it is okay. Okay, after that, what you will do, we will decide the spacing of second stiffener. For example, when we are solving, I will give the example, but here let me show you this. So first, we have decided the spacing of first stiffener. For example, this spacing. This is a bearing stiffener, so we have decided the spacing of this stiffener. Please hold on. Okay, after deciding spacing of first stiffener, we need to decide the spacing of second stiffener if required or not. So we will see that maybe let's suppose I'm deleting this or I'm just showing it over here. So we have decided the first stiffener. So you will see that shear force is reducing along the length, and in the center zone, applied shear force is very less. So if I want to decide the spacing of stiffener in this panel, so maybe first I need to check the shear capacity of web without stiffener. Maybe the shear capacity of the web without stiffener may be more than applied shear. So we will check that whether the second intermediate stiffener is required or not. So how we will do? First, we will decide, we will compute the shear capacity of web without stiffener, and we will compare that capacity against the applied shear in this panel. So in this panel, we will see that where the applied shear is maximum. So applied shear is maximum at this end. So we will check the So calculate VU maximum within the portion between already designed intermediate and bearing stiffener. So check whether intermediate stiffener are required or not. For this case, calculate CV value without stiffener. So what we will do, we will compute the shear capacity of the web without stiffener. So if we are not providing the stiffener, then KB value will be equal to 5. Already we have discussed. So here also, so KV value is equal to 5. So if we are not providing the intermediate stiffener. So if KV value equal to 5, then if you are substituting KV value 5 in this equation without stiffener, so E value is 200,000 and KV value is equal to 5. So 200,000 multiplied by 5, answer will be 1,000 or maybe 1 million. So if you are taking the square root of 1 million, so answer will be 1,000 and 1,000 multiplied with 1.37 and it will give the answer 1370. So the expression for KB value equal to 5 or which is for the case if we are not providing stiffness. So this value parameter will become this one 1370 under root f over y under root f of y. So this expression is the same one, but for kV value equal to 5. So if height of the web or thickness of the web ratio is less than this parameter, then you need to determine the CV value from this expression. So this expression is also simplified for kV value equal to 5. If kV value equal to 5 and E value is 200,000 megapascal, so this expression can be simplified for kV value 5 and by substituting the E value, so which will yield this answer. So If H over TW ratio is less than 1370 under root Fy, so you will have this case. So CV value will be computed from this expression. So this expression is also simplified by substituting the kV value 5 and E value 200,000 megapascal. Question number 3 and 4 are simplified for kV value equal to 5 and they are given here. So depending upon the case, whether you will have the elastic buckling or inelastic buckling, you will determine CV value without intermediate stiffness. So when you will have CV value from any one of these equations, depending upon this condition, you can determine the shear capacity. And shear capacity will be equal to 5V area of web, 0.6 Fy shear strength and CV value. And if this after 10 minutes. Okay. So capacity is more than applied shear and height of the web over thickness of the web ratio is less than 260, then we do not require intermediate stiffness. So if these two conditions are satisfied, no intermediate stiffness are required because the web capacity without stiffness is more than applied shear. So this formula is also the simplified version. So if VU is less than 815.4 over height of the web over thickness of the web ratio square into area of web. So for 836 steel, considering K value is equal to 5 and finding CV from equation number 4. So no need to check this condition. You have already checked this condition. So if actually this formula is simplified from here because we have compared these two conditions. So if these two conditions are satisfied, we do not require intermediate stiffness. But again, AISC recommend that even though the stiffeners are not required, so we need to provide these stiffeners at a maximum spacing of 3H. So stiffener will be provided at a maximum spacing of 3H, even though the stiffeners are not required. Or what does it mean? If spacing of the stiffener is more than 3H, so we will assume that the stiffener, they are not contributing to the shear strength. But if this condition doesn't satisfy, capacity of the web without stiffener is less than applied shear, then we need intermediate stiffener. So we are having the two formula for maximum spacing of stiffener. So first we will try to provide the stiffener at maximum spacing. So these two formula we are already familiar with. So these are these two formula. So we will compute the spacing, maximum spacing out of these two formula. And the least answer out of these two will be spacing of stiffener or second intermediate stiffener. So A is lesser value out of these two. So we will compute the A value from here. If we know the A value, then we can compute the KV value by using this equation because we have provided the stiffness at maximum spacing. So if we know the KV value, we can compute this parameter 1.37 under KV over Fy because we have decided the spacing of stiffness corresponding to maximum spacing. We have computed KV, and from the KV you can compute this parameter. If height of the web over thickness of the web ratio is more than this parameter, you will compute CV value from equation number 2. If height of the web over thickness of the web ratio is less than this parameter, then you will use equation number 3 for this CV value. And then if you know the CV value, then you can determine the shear capacity by this formula. Since we have provided the intermediate stiffness, so we can also consider the reduction also. Okay, here an important point is that for the first intermediate stiffness, we are not considering tension reduction because at the end applied shear force is larger. So we want to have more factor of safety. So for the second intermediate stiffness, we can consider the post buckling strength enhanced by or contributed by tension reduction. So CV prime value will be computed by using this equation, which is the function of CV value and A over H ratio. So at the end, we will compute the shear capacity, including stiffness, and by considering tension reduction due to provision of intermediate stiffness, and we will compute the capacity. If capacity is more than applied shear, then okay. If this condition does not satisfy, we will reduce the A value that you have selected here. And for the reduced value, you will recompute KV value, and then we will recompute CV and CV prime until the capacity becomes larger than VU. Okay, here there is a new modification in the book. This parameter 0.6. This is the parameter that we use to convert the shear strength into normal strength. This parameter 0.6 is in AISC code, but ASHTO says that this parameter 0.6 should be computed by this equation. So the factor 0.6 is equal to 0.58 R value in ASHTO LRFT. So if FU is less than 0.755 FY, then R value is equal to 1. What is the FU? FU is the ultimate strength of stiffening or the stiffener plate. Fy is the yield strength of stiffener plate, and phi F is the strength reduction factor for flange in flange, which is 0.9. So strength reduction factor for flange that we have computed in our in computing the bending capacity of flange. If this condition doesn't satisfy, then you need to compute R value from this given equation. So Fu is the maximum stress in compression. So, and FCR is the factored flexure resistance of compression flange. So Fu is the ultimate strength of the compression flange. So if we are using the 836 material, so the flange will fail when Fu will be equal to 400 megapascal for 836 steel. And FCR value, you might be remember that when we computed the flexure capacity of plate girder in proportion of plate girder, so FCR value is based upon later torsion buckling or flange knuckle buckling, whichever is the lesser. So that is that FCR value that we use to compute the flexure capacity of compression flange. So then we need to compute the R value accordingly. But for this cases, you can still consider this factor 0.6 as it. But in actual design in the field, so it is recommended to compute this parameter, not 0.6, rather by this parameter. Because this parameter is always normally between 0.6 to 0.5 to 0.58. It is less than 0.6. So you can still use this parameter 0.6. So no need to consider for the examination. So if the capacity is more than VU, then spacing is okay. Next is that we need to compute the area of stiffness. But if capacity is lesser, then we need to reduce the spacing of stiffener. Then we need to recompute kV value for the reduced A value. Then we need to compute CV prime and CV value and recheck the capacity. Until if the capacity is okay, then spacing will be final. Otherwise, we need to keep on reducing the A value, and then we need to determine the appropriate spacing at which the capacity should be more than V. So after that, there is AISC says that we should discontinue the intermediate stiffener from the tension flange side. So we discontinue this stiffener, we provide a gap between 4 times of thickness of the web to the 6 times thickness of the web. Why it is provided, I will explain in the next slide. So a solid or a continuous weld is provided to connect stiffener with the propellant, and intermittent weld is provided to connect the stiffening plate with the web. And then we discontinue the flange plate, stiffening plate from the tension flange. Why? There is a reason. Either we discontinue or we provide a gap or a hole at the junction. So why we do this? For example, if we provide a weld here, so for example, this is the junction, the corner where the stiffening plate, web and flange are meeting. So let's suppose this is the weld which is connecting the flange plate with the web, and this is the weld which is connecting the stiffening plate with the web, and this is the weld which is connecting the stiffening plate with the flange. So if all the weld they are meeting at this one point, so actually this weld is designed to resist the shear between web and flange, which is very large, and this weld is provided to transfer the forces from the flange to this stiffener, and this weld is designed to transfer the shear forces from this flange, this web to this stiffener. So actually, this web is subjected to a larger forces. So when all these three welds they will meet at one point, or they are merged. So the forces, shear forces which are developed or which is resisted by this weld, that will also transfer to this weld. But this weld is not designed for this shear force. So the shear force which this weld is resisting, when it will transfer to this weld, then they will break this weld. So they will cause the cracks at the junction. So just to avoid this, or just to avoid the stress triaxiality, because this weld is also subjected to the forces which are developed in this weld. Some of the forces are also transferred from this weld, and some forces they will also transferred from this weld. It means that any one weld is subjected to three forces, but all the weld they are only designed for one forces. So how we can avoid? By providing a gap here. When we are providing the gap, so all the three welds they are not joining at one point. So they are not transferring the force from one point to other point. So how we can do? Either we provide a gap at this junction near the tension flange, or we discontinue the intermediate stiffener from the bottom side at a distance 4 times to 6 times of thickness of web. Okay, next is we are actually I'm explaining the same procedure which is over here. Now I am over here. So next is we need to decide the cross section area of stiffener. So actually we have discussed this equation already. Here it was. Yes. We will compute the IST1 from this equation. So J value is computed from here because we know the A over H ratio. So J value is computed. B value we also know which is the lesser out of the spacing of stiffness or height of the web and thickness of the web cube. So IST1 is equal to this one. And we are equating this expression with moment of inertia of one stiffener. The moment of inertia of one stiffener about its own centroid will be B into T cube divided by 12. If B is the width and thickness of the stiffener is TST, the moment of inertia is B T cube divided by 12. But that is the moment of inertia of one stiffener about its own centroid. But we want to compute the moment of inertia of the stiffener along center line of the web. If we are assuming thickness of the web is equal to 0, so in other words, we want to compute the moment of inertia of this rectangular plate about its base. So moment of inertia of a stiffening or a rectangular about its base is equal to B T cube divided by 3. So B T into B cube divided by 3 is the moment of inertia of one stiffener about its base. So if they are two stiffeners, so we need to multiply it by 2 because we also need to compute the moment of inertia of this stiffener about this center line about its base. So T B cube divided by 3 is the moment of inertia of the one stiffener about center line or about its base. If we are computing about its own centroid, then that will be T into B cube divided by 12. But we want to compute along the base or center line. So that's why this is BT cube, TB cube divided by 3 multiplied by 2. And IST value is equal to JB into thickness of the web cube. So by solving these two equations simultaneously, so you can compute, you will have this equation. So this equation actually got by solving these two equations simultaneously. JB thickness of the web cube with by equating with this parameter. Anyhow, B over T ratio for our stiffener plate should be less than 0.56 under root E over Fy, which is approximately taken as a 15. So, but ASTO gives that B over T ratio of this stiffening plate should be less than 13.58. But we are following AISC. But in design or in the field, you can also use this ASTO. So, for A36 material, this parameter will be 15. So, this expression has been developed by the same concept that we have used by in proportioning of length. If you multiply this B over T ratio with B and divide it by the B, then you will have this expression. So BSD is computed from this parameter because AST minimum you have computed and AST minimum you have computed by using this equation. The formula is supposed to be here. Yes, you will compute the AST minimum from this equation. And then after deciding the B and T value, you will recompute B over T ratio. So it should be less than 15. So you know the J value and IST minimum you will compute. So you will compute IST1 by this equation because you have already decided the B and T value from here. So this IST should be more than this I minimum. If this IST is less than I minimum, then you need to revise by using this equation. So then you will need to revise the B value by using this equation. And when you will determine the updated B value, then you will determine the updated thickness of stiffener by maintaining B over T ratio less than or equal to 15. And then one step is missing. We need to check this case. That we have discussed this case. IST should be more than this parameter. So you need to compute IST2, and that I will explain when we are designing this technique. So this case must be satisfied. IST2 is this one. So after deciding the area of stiffness, the last step is that we need to design the weld, and I have already explained you that we need to provide the continuous weld over here, but we will provide the intermittent weld to connect the stiffening plate with the web. So what we will do, we will provide the intermittent weld, and we need to decide the spacing. And length of the weld we may kept equal to LW minimum. And what will be the design force that will be used to design this weld? An empirical formula is suggested by AISC. So design shear flow is computed by this parameter 0.045 divided by 1000 into 8 under root f y cube over E value. And for a 36 material, this parameter will become like this. So this is the shear flow. So if we are providing the bolted connection, then the spacing of the bolted bolt or the rivet should not be more than 305. If we are connecting the stiffening plate by the fastener with the web. But if we are providing the intermittent weld, then spacing of the weld should not be more than the lesser value out of 16 times of the thickness of the web, or 250. So if thickness of the web is 10, so 16 times of thickness of the web will be 160. So 160 is less than 250. So it means that spacing should be not be more than 150. So we will provide intermittent weld corresponding to LW minimum with maximum spacing of 16 time of thickness of the web or 250, whichever is lesser. So I will stop here. So next time we will start example number 6.2, and we will carry out the design of intermediate stiffness, where we want to select the spacing and the cross-section area of stiffness. So I have already downloaded one attendance earlier, so I will compare later on. So please raise the hand, all the students who are present. So Haris Chaudhary, where are you? Mr. Haris, Hubab, and Mirza Muhammad Sarfaraz. CR, are you there?
Yes, sir.
ये रोल नंबर नोट करो इसके ये निशाम ये मैं है था इधर भी और मिर्जा मोहम्मद सरफराज इनके रोल नंबर नोट करो ठीक है मुझे टेस्ट करो
Okay, sir.
So I will conclude the lecture. Inshallah, I will see you on Friday.